So in the in the last lecture, we have covered some basic reactions and their stereochemistry and some special problems of a reaction related to carbocation. And we are going to cover the next topics, that is hydroboration, oxidation, and oximercuration, demarcuration probably in this lecture. Okay. So first topic, our today's first topic is hydroboration oxidation. Hydroboration oxidation. First, we will observe the reaction hydroboration reaction. Simply, hydroboration reaction is a very unique reaction. First, let's understand some basic things about the reaction. Write with me some basic things. First, in this reaction, syn addition occurs. Syn addition. Second, no complete carbocation formation. No complete carbocation formation. That means no rearrangement of carbocation, no rearrangement or ring expansion, contraction occur. Okay, so no complete carbocation formation. So you have to understand that in this reaction, no rearrangement or ring expansion contraction occurs. Okay, the reagent is B2H6 or BH3, BH3 or R2BH or RBH2. That means with boron, at least one hydrogen should be there. Okay. With this, step one is this. This is first step. This is hydroboration step. Hydroboration step. And next, in second, 2. In 1, you can write this. In 2, H2O2 NOH. This part is basically oxidation. So overall hydroboration oxidation. And the last statement about this reaction is boron will attach more electron rich carbon. Why boron? Why boron will attach to more electron rich carbon? Boron is from BH3 or B2H6. Because boron is a Lewis acid. Compounds of boron are basically electron deficient compound. So electron rich system will prefer to attack that, as boron is Lewis acid, right? Now in this reaction, what happens? From alkene, suppose one alkene is given, this alkene will be converted to alcohol. Alcohol. And here anti-Markovnikov rule applies. Anti-Markovnikov rule is applied. That means OH is attached to the less substituted carbon. Less substituted carbon means less substituted carbon. That means in alkene, suppose here is one methyl group. I think there was a network problem in the last video. Okay, so I think there was a problem in network. So okay, I am repeating this. So boron will attach to more electronegative, more electron-rich carbon. Electron-rich carbon, why? Because boron is a Lewis acid. That means electron-deficient compound. That's why it will more preferably attached with electron-rich carbon. What happens in this reaction? One alkene is given, and with this alkene, if we treat these reagents we will be getting OH at more substituted carbon. This is called Markovnikov rule. If we were getting product this would be Markovnikov rule product, but here anti-Markovnikov rule is applied. We will see how it is attaching like that, or why anti-Markovnikov, how anti-Markovnikov. Anti-Markovnikov rule says the OH group will attach to less substituted carbon. Less substituted carbon means, suppose we have propene molecule, or suppose we have uh, this particular molecule. Here, this is one alkene carbon, this is another alkene carbon. First alkene carbon has one substituted group, methyl. So this has one substituted. And the right hand side alkene carbon, this has two substitution. So there is two substituted carbon. So second carbon is more substituted. Here the reagent, what does it do? It attach OH to the less substituted carbon. So from this molecule, our product will be OH. Okay, OH at less substituted carbon. Now, boron will attach to more electronegative carbon. How we will recognize that which carbon is more electronegative? Suppose my alkene is this. We are showing this reaction with asymmetric alkene, because symmetric all the sides are same, because no point of discussion. Okay, here in two ways you can identify that which carbon is more electron rich. First, break this pi bond to plus and minus. First, put here plus, here minus. Second, put here plus, here minus. Now check stability of carbocation, where more stable carbocation is formed. Here carbocation is 1 degree, here it is 2 degrees, so it is more stable. So in the more stable form, more stable carbocation, this center is negatively charged, right? So this center is electron rich, more electron rich. So in this way, by differentiating by heterolytic cleavage method, you can identify that which carbon is more electron rich. That means in which carbon boron is going to attach. Another method is check hyperconjugation or resonance. In this molecule, we know hyperconjugation is there. These three hydrogen will show hyperconjugation. Now, make one hyperconjugative structure. If you try to draw one hyperconjugative structure, what you will draw? You will put like this. In second one, you will put like this. In third one, you will put like this. So in every time, electron is getting accumulated in this particular alkene center. So this method is also saying, hyperconjugation method is also saying that this center is more electron rich. So two methods you are getting. Okay. One is heterolytic cleavage method. It is for your understanding only, okay, so that you can easily identify heterolytic cleavage method. So here cleave heterolytically, then check the uh, stability of carbocation, and in that structure the center which is negatively charged, so in the actual structure that center is more electron rich. Second method is hyperconjugative method or hyperconjugation method. Okay, hope you have understood this. Now let's go to the mechanism. Okay, in another slide I am starting again the mechanism. This is the most important thing. Now we have understood that which center is more electron rich. In the reagent, if B2H6 is there, B2H6 means dimer of BH3. So this is basically 2BH3. Whatever reagent is given, at least one hydrogen should be there. So you have to write that particular reagent like this, HB something. Here BH2. If it is 2R, so HBr2 or HBHR, like that. Okay, you have to separate that one hydrogen. This is needed. Now we know this center is electron rich. So this center is going to attack BH2. What will happen? BH2. Here positively charged H. But in the statements, In the initial, when we started the discussion, I have told you that no complete carbocation is formed here. So this is not formed actually, but for your convenience, you can write that. After that, what will happen? Negatively charged. This hydride will attack there. So what will happen here? BH2, here hydrogen. So this thing, this carbocation is not formed. What actually happens is here, suppose double bond, single bond, and H BH2. Reaction occurs like this. From here, BH2 H. This transition state, through this four-member cyclic transition state, this compound is formed. This is actually four-member cyclic transition state. You write four-member cyclic transition state. So from four-member cyclic transition state, this alkyl borane is formed. It is alkyl borane. This is nothing but BH2. Okay, this is the first step. Now what will happen? We can write this as H B H propyl. This is actually propyl group, and boron and two hydrogen. So propyl group, boron and two hydrogen. We can write it like this. Now, 1 minute, let me see recording is actually going on or not. Uh, okay, okay, fine. Now again, this the product is itself like a boron, and it can again react with this alkene like this. Okay, now what will happen? Again, four-member transition state, B H, and propyl group is like this, and again this can react with another molecule of sorry, yes, another molecule of propane, and this will again lead to B propyl propyl propyl. That is tri-alkyl group with boron. This is actually trialkyl boron. Trialkyl boron, Br3. Okay. So in this way, our trialkyl boron compound will form. Right. Now, first step is done. Okay. So in first step, our propene BH3 is giving these three. Okay, trialkyl boron. In the second step, here H2O2 and NaOH will react. H2O2, hydrogen peroxide, and NaOH. NaOH means actually OH minus base. This will simply attack here, and HOO minus will form. HOO minus. This anion is called hydroperoxide ion. Hydroperoxide ion. And boron is electron deficient. Okay, so this will go and attack simply this boron. What will happen? Suppose B 3 propyl group, I am writing like R, and OOH, this is attached. Now boron is negatively charged. Now what will happen? This R group will migrate to that oxygen, and OH minus will remove. So what happens? B OR R R. Simply another OOH, another hydroperoxide ion attacks, and another R migrates. So again, B, OR, OR, R. Again, another OOH minus, again migration. So B, OR, whole 3. Trialkoxide boron, this is formed. Now in hand we have B, O, isopropyl, O, isopropyl, O, sorry, not isopropyl, N-propyl, N-propyl. Okay. Now that OH minus that was removed, okay, 3 OH minus, in every step OH minus was removed. So OH minus, what will happen? Well, OH minus will attack there and this will remove. So from this part, what will happen? OH, O minus, and from OE, and it will abstract proton and it will give ultimately OH, ultimately sorry, N-propyl alcohol. Again another mole OH will attack there and third mole of OH will attack there. Okay, so 3 mole isopropyl alcohol. So from this molecule we are getting this OH. Now in the whole scheme, this molecule is, we have taken 3 moles. Okay, in the previous slide, if you look that in every step we are using one alkene. So 3 mole alkene overall we have used, and so 3 mole alcohol we are getting, but we have used that BH3 or the boron molecule 1 mole, isn't it? So 3 molecule alkene is giving 3 molecule of alcohol using 1 mole of BH3. Okay, in this final product, this hydrogen is coming from BH3. If you closely observe the first initial stages where trialkyl boron is formed, in every step this particular hydrogen is coming from this boron only, and this particular OH is coming from H2O2 NaOH, isn't it? Mainly H2O2. So if in this reaction, instead of BH3 or B2H6, if I give B2D6 and H2T2, sorry, T2O2 tritium, NaOT, then product will be DOT. Okay, nowadays in examination the simple mechanism or the simple product nobody asks. Okay, so if you skip the reaction, you can simply tell the product, but examiner what will do, it will substitute the reagent with some heavier isotope. Then if you don't know the mechanism, you will not able to solve that. Okay, so simply mugging up the actually reactant and product and looking upon some trick, this is not going to work. We have to understand the mechanism. I don't know, there is network issues actually. Okay, so you have to look upon the mechanism very carefully so that you can solve all the questions. Okay, now whatever information you have received till now, try to answer this question. To oxidize 2 mole of alkene, how many moles of BH3 is needed? We have to oxidize 2 mole of alkene, and how many mole BH3 is needed? Here in BH3 and the oxidize, this two term indicates this is the question of hydroboration oxidation. So here 3 mole alkene, 3 mole alkene gives 3 mole alcohol. We have to use 1 mole of BH3. Then to oxidize 2 mole of alkene, 1 by 3 into 2. Answer is 2 by 3. This will be answer. Okay. Hope you have received, if I've understood this properly. Now, another question for you. Styrene, step 1, BH3, step 2, H2O2, NaOH. First, BH3 will attach, BH3 addition. More electron rich carbon will be getting that boron. So, this resonance is pushing the electron density towards this carbon of the alkene. This is our alkene. Here, the reaction will occur. Now, this carbon is getting more electron density because of this resonance, isn't it? So, this carbon will get boron part. So, in the first stage, BH2 and basically hydrogen. And in whatever mechanism in the products, if you closely observe that the carbon, uh, the carbon where BH2 was attached, that carbon was getting OH actually. Finally, that carbon was getting OH. So our product is this one. Okay. And the hydrogen is this. This hydrogen is coming from BH3. And this is the OH. So simply this one. Another question you can try. This one. Here simply this hyperconjugation will push the electron density over this center. In some books also it is written that this is sterically driven. That is, you have to put more, you have to put electron density to the less hindered carbon, steric hindrance. So advanced books will tell you that this is not sterically, this is electronically uh, driven. Electronically driven means you have to look upon not steric hindrance, just on electron reach, which center is electron reach, nor not which center is electron, which center has less steric hindrance, not like that. Okay, you have to look upon only the electron cloud on carbon, on which carbon of alkene there is more electron density, that center is going to graph the boron. So here BH2, simple. And BH2 and that hydrogen actually is going, scene addition I have told you. Another thing you can look upon, this 4-member transition state, boron and H is adding up from same side. So this is basically scene addition. So in this structure, BH2, in this structure, BH2 if above the plane, corresponding hydrogen will also be above the plane. Then this carbon had one methyl group, this methyl will be below the plane. Plus another structure possible, which is if BH2 is below the plane, hydrogen will also be below the plane and methyl will be above the plane. Now OH will be simple, oxidation will add BH2 will be changed to OH. This will be changed to OH. So these two products will be formed. Okay. So that's all for oximercuration, demarcuration. Next, sorry, not oximercuration, demarcuration. Uh, our hydroboration oxidation is over. Okay. Next, oximercuration, demercuration. Oximercuration, demercuration. People write in short form OMDM. So write some features about this reaction. First one is it is anti-addition. Second point is same, no complete carbocation is formed. That means no rearrangement or no ring expansion contraction occurs. Third, reagent is AgOAc whole 2. AC group means C double bond O CH3. This is AC. OAc means OCOCH3. Okay. Now, fourth point, sorry, the first step reagent is this. The second step is NaBH4. NaBH4 water. This is second step. First one is oxymercuration. Second one is demarcuration. Marcuration comes from mercury. First, oxymercuration means mercury is going to add with oxygen. Oxygen is going to add and mercury is going to add. That's why oxymercuration. And next step is demarcuration. That means mercury is going to detach. That is demarcuration. But mercury will detach, oxygen will not. Okay, so oxymercuration, oxygen and mercury is adding. Demercuration, mercury is getting removed, so oxygen is remaining with the compound, with the product. That is basically making alcohol, isn't it? So here what will happen, this is suppose our alkene. From here product will be OH, this one will be product. So here anti-Markovnikov of rule will not be applied. This is simply Markovnikov rule. Markovnikov rule, that means OH will attach to the more substituted carbon. Okay. Similarly, mercury is also electron deficient and it will attack to more, it will be attached to more electron rich carbon. Simply. But this is anti-addition. BH3 was added in syn fashion from same side, but this is going to attach in anti fashion. How? Let's look upon this. What will happen? Suppose this is our same alkene. Reagent is HgOAc whole 2. This alkene will attack more electron rich, means this center. This will attack to mercury and one OAc will be removed. Okay. So what will happen? HgOAc. Okay. Now this will be positive. So not complete carbocation is formed. I have told you. So with this, with no delay, with no time lapse, this will attack. So this carbocation is actually not forming. This is occurring simultaneously. Okay, this thing is happening simultaneously. So this will not form actually. Finally, what we will get? This three member, like bromonium ion, like mercury. I don't know what is called, but this is like bromonium ion only. This is OAc. So this is our actually product after oxymercuration. Here will be one positive charge. Okay, when mercury is donating electron, so it is positively charged. So this is our actually oxymercuration. uh not this, even water will attack there. Water will attack in which center? Water will attack obviously this center, like bromonium ion I've said. So HgOAc, methyl OH. So this is going to be our oxymercuration product. Oxymercuration. Next step, demercuration will occur in NaBH4. NaBH4 demercuration will be occur. Now, how the demercuration is occurring? This is a very important thing to notice. What will happen? Let's understand. Suppose this overall structure, let's consider it as RHgOAc. Okay. NaBH4 means Na plus BH4 minus. BH4 minus I can write B bond BH3 minus Na plus. This is actually NaBH4. Now what will happen? This H hydride will attack there and OAc will remove. So R Hg hydrogen. Right. What will happen? Homolytic cleavage will occur. So R dot plus Hg H dot. Okay. Now again another molecule of RHgH from a similar parallel reaction. This R dot will attach, will take up this hydrogen. This bond will again homolytically cleavage. This will lead to RH plus again RH dot. In every step, RH dot will be formed, and RH we are getting. So we are finally getting RH. So this RHGOSE, we are getting RH. So that means this portion is replaced by H. H from NaBH4. So now our product is simply OH, H. So this H is coming from NaBH4. Okay. And OH, OH, this is coming from water. So you can try by higher substitution. Okay, you can use NaBD4, then deuterium will be there. Okay, so this is the simple reaction. Practice 2 or 3 times by yourself, and you will grab the concept, or you will get a flow. Okay, next, let's solve some questions. Similar kind of question. My question is this one: AgOSC whole to water A, then NaBD4. Okay, so you can try. It will occur like, first it is anti-addition, and mercury is going to attach to more electron rich center. This center is more electron rich because methyl group will pushing the electron by plus H, and this will electron rich. So this center will be getting above the plane. Suppose uh, above the plane, suppose HgOSC. Then as it is anti-addition, so below the plane it will be OH. Okay, below the plane it will be OH. And here methyl was there, so methyl will be above the plane. Opposite case is possible. If HgOSC is below the plane, OH will be above the plane, and this methyl will be below the plane. So this another structure is also possible. I am showing you from one structure. Whew. Okay, now NaBD4, this will add deuterium to HgOSC position. So finally our product, we are getting OH here, deuterium, plus another products above the plane, below the plane will be deuterium. So above the plane will be OH. Okay, so this two structure is possible. This is our actually final product. Now a special case of alkyne. From alkyne, suppose I have one alkyne. Suppose this is written, this is alkyne. In alkyne designation of linear form, if some alkyne is given like this, that means here is one carbon, here is one carbon, here is one carbon, here is one carbon. That is actually C triple bond C, CH3, CH3. But here it means carbon, carbon, CH3. Okay, so CH3, CH triple bond C, like this. If we are doing this particular reaction, first what will happen? 3-member cyclic ring will form, HgOSC plus, but here 3-member, but there will be one double bond. Now water will attack. Simple, water will attack to this center. Some game will change. Game will change from these only. Methyl OH double bond HgOSC, right? Enol is getting formed. Okay, this is enol, isn't it? Enol is getting converted to keto now. This bond will shift there, and this will shift there. Double bond O, HgOSC. So this hydrogen actually in enol form, OH double bond. What do we have to do? Break this bond, and here you will get the negative charge, and add this hydrogen to that center. Okay, so C double bond O, CH. Okay, so this is our enol form. And now NaBH4 or NaBD4, NaBH4 will add this hydrogen in that particular center. So double bond O. So this is giving simply acetone molecule. Okay, Now, one very important question, and the most important question of the session. Most important question. Question is phenyl, phenyl ring C triple bond CH. In one reaction, it is given Hg OAC whole 2. Okay. In another reaction, it is given Hg OAC whole 2 NaBH4. Very important. In the previous reaction, look at carefully. In this particular reaction scheme, we have not used NaBH4, right? In oximercuration and demarcuration, we have just used the reagent of first step, not the second step. Make one correction in that particular stage. HgOAC whole to add water with that one. Okay. In the second step, add NaBH4. Okay. NaBH4, similar reagent, similar reducing reagent, they can use LiLH4 or ZnBH4, etc. So boron hydrogen should be there. Boron and hydrogen should be there. Or aluminium hydrogen. Boron hydrogen or aluminium hydrogen. This should be there. Si alpha 2 BH. This is one kind of reagent. Boron hydrogen is there. Okay. Now let's come to this problem. The last problem of this session. AgOAC whole 2. AgOAC, simple AgOAC whole 2. We have previously seen that this will be going to add OH in this position. So we will be getting this similar to previous one. The name of the compound is acetophenone. Acetophenone. It is the product when we do Friedel-Crafts acylation in benzene. Okay. But what will happen in this? In the first stage, simply pH C double bond O H. And if you have read reagents a little bit, you will understand that NaBH4 is reducing reagent. It is source of H minus. It will attack to this position and it will open up like this. So we will be getting pH H, this hydrogen, and here O minus, and again it will abstract proton from any source, from water, or we will do workup. Overall we will be getting this. So this is our final product. Don't just look upon these reagents and don't consider in exam that this is oximercuration demarcuration, so let's add OH there, and then analyzation, let make analyzation. So in exam, if you don't know this, you will definitely do a mistake by making this product only. Okay, so here the product is this. Don't get confused. I hope I have told almost everything about the oximercuration demarcuration and the hydroboration oxidation. Okay, so I am ending the session here. In the next class of carbocation, we will be discussing thoroughly phenol-phenolone rearrangement of rigid system, non-rigid system. Uh, there are three types of rigid system. There are two type of non-rigid system. Everything we will going to observe in the next reaction. We will complete phenol-phenolone rearrangement, and next we will be covering diene phenol rearrangement. Okay. Till then, have a nice day. Keep learning. Bye bye.